This device is called a simple pendulum. And as you can see, all the mass is pretty much concentrated at the end of it. We have a very lightweight string connecting that mass to our pivot point. So let's go through the force equations for this to see if we can justify this being simple harmonic motion. And then we'll look at an experiment students have done in order to figure out if there's a relationship between period and any variables that have to do with this pendulum, like length or mass or things like that. So let's look at a free body diagram or force picture for that pendulum when it's off at an angle. I've got a downward gravitational force and I've got a tension force pointing towards the pivot. I'm going to do like I do for circular motion. I'm going to call the r-axis along the radius of the circle this is tracing out. I'm going to call the t-axis tangent to that circle. What I want to do is I want to look at the net force along the tangent direction. Usually we've looked at radial for circular motion. So the only tangential force is the component of Fg that is tangent to the circle. So I've written sigma F equals Fgt for Fg tangent. And from that little triangle there, we could see that that will be Fg sine theta or mg sine theta. Notice I put the little negative there because the farther we go in one direction, the more acceleration we'll have back the other way. Gravity here is actually going to take the role of restoring force. So at first, ma equals minus mg sine theta doesn't look like the form we'd expect for simple harmonic motion. We've seen that we need a, or the second derivative of position, to be directly proportional to position itself, with a minus constant b of some sort in front. We don't have that there. But if sine theta was replaced with just theta, we'd be getting a little bit closer to it, since we know theta and x have this relationship. It turns out that as long as you don't pull your pendulum too far to the side, sine theta and theta are approximately the same. I had my class at Southmore in 2015 check this, and we looked at angles from 2 to 20 degrees. We looked at their value in radians and their value, or the value of their sine, and you could see they're pretty close as long as the angle stays small. So when we take the small angle approximation, we actually can say sine theta and theta are the same thing. So that gets us to this point. ma equals minus mg theta. Obviously mass cancels out. And that's going to have pretty serious implications later on, that mass doesn't matter. Notice I've also subbed in, instead of a, I've replaced it with r alpha. We know that's the conversion between a and alpha, as long as there's no slipping. So I get the equation r alpha equals minus g theta. And that looks a lot like what we expect for simple harmonic motion. So if there's theta, I take the first derivative to get omega. I take the second derivative to get alpha. And then I can just plug in theta and alpha. And I end up with an equation where almost everything cancels, just like before. And what's left can be rearranged to solve for period. So that is the equation for the period of a simple pendulum. One thing I like to have students do is predict all the variables that would affect the period of a simple pendulum. Here's a list a class at Southmore came up with in 2015, and I like this list because it's a pretty comprehensive one. We went through and looked at which ones would be simple to measure. Some of them, like the speed or the energy or things like that, taking a direct measurement would be hard. But length, mass, initial height, amplitude, those are all things we could probably do. We can't really do gravity. We can't go to a different planet. The two I asked students to look at were length and mass. I told them we couldn't do any of these because small angles were important, and you just saw why small angles are important. So ultimately, I asked students to find out this dependence and to design an experiment to do it. So they run off and they try different lengths and see what this graph of period looked like. They try different masses and see what this graph of period looks like. So here's some data a class in 2012 at Southmore came up with. We saw that changing the length of string definitely caused a pretty significant change in how long it took to do one complete back and forth. Notice we had them time 10 and then divide by 10. That's because timing one back and forth is too hard to do. Here's the data for mass, and you can see that changing the mass didn't have a huge effect on how long it took for a back and forth. If we graph that data, we could see varying the length, we had a definite positive trend. Varying the mass, it stayed almost constant. But I think you guys know why that is. So here's the equation we had for period. And as you can see, mass isn't in the final equation. And the reason it's not in the final equation, even though we started with sigma f equals ma, is it was on both sides. So it canceled. The more the pull of gravity got by increasing the mass, the lazier it got too. And it canceled out. So it's nice experimental verification of some of the math that we're seeing. And like before, you get this equation by writing sigma f equals ma or sigma torque equals I alpha, and using this relationship between theta and alpha or between x and a to plug in.